All right, welcome. So we're going to start now with chapter 1 of the book, and I figured I would just kind of mostly use the author's words to talk about what this book is about and the motivation. So it's 2 pages, and just going to kind of hit the highlights here. Okay. So Kevin Murphy says, much of current machine learning focuses on the task of mapping inputs to outputs. Yeah, that makes sense, right? So we got some function x to y. And Judea Pearl, well-known AI researcher, has called this glorified curve fitting. Okay, so the author says, well, in high dimensionality, that might be a little bit unfair. But the notion is, if we're really focused on prediction of observable patterns, and not so much focused on the understanding of the underlying latent structure behind these patterns, then that's where sort of the quote of glorified curve fitting fits. Okay. And so this is where, if you do something like a linear regression and you just sort of have a point estimate of your best parameters, theta, okay, you can do that. You can, you can take a linear regression and you can just get, what are the coefficients. But if you think about it from a probabilistic point of view, then not only do you have that best estimate available to you, then you also have things like the standard error. You can look at the distribution of likely values around that centered prediction. And then if you go even further into areas that, frankly, I'm not really all that well versed, but there are forms of robust regression where you do something and you want your regression to be more robust to outliers in your training data, and there's other things, and so again, I think that this I'm excited that this book will allow for more robust interpretation of the different techniques that we talk about. So continuing, gaining a deep understanding of the structures behind the observed data is necessary for advancing science. Example is healthcare, where identifying the root causes, the mechanisms behind the disease, not just the symptoms, but the mechanism behind it, is the key to developing cures. Okay, we're not going to get into a side conversation about Western medicine just treating symptoms and not actually, that could be a whole nother session where we just go down the rabbit hole. So the author says, by robust, we mean methods that work well even if there are unexpected changes to the data distribution to which the system is applied. That's pretty hard to achieve in practice, but we get the concept, right? And so you think of an area like robotics. And by efficient, we generally mean the data, we mean data or statistically efficient, okay? And so here he's talking about learning quickly, so sample efficient algorithms. He notes at the end that we are also interested in computationally efficient methods. That's got to be a consideration, but that's not sort of the primary focus in this book, okay? So really looking at, hey, if we can understand the latent structure, then we may be able to extrapolate beyond the data we've seen. And if we are sample efficient, then we can learn quickly. So those are his 2 main criteria. So to develop robust and efficient systems, this book adopts a model-based approach. So we want to learn parsimonious representations of the underlying data generating process given samples from 1 or more data sets. So if you can understand the data generating process and what distribution of values it can output, then you get the things that the author's talking about in terms of these nice robust algorithms. One way to formalize this process is in terms of Bayesian inference applied to probabilistic models. So I think that pretty much encapsulates the author's focus for this actually 2-book series, right? We're just looking at book 2. All right. Once we have a set of inference methods in our toolbox, then we'll broadly consider 4 main kinds of tasks: prediction, So classical classification regression problems, generation. So you can imagine diffusion models generating images, right? Discovery. So this is finding latent structures behind things, and control. So optimal decision-making, a little bit of reinforcement learning at the end of this book. So how the book is organized, we have part 1, fundamentals. Did I skip over something? So part 1 is the fundamentals. So we got a few chapters to go through that. Then we're going to talk about inference. So that's where he talks about Bayesian inference applied to probabilistic models. Okay, then the rest of the book breaks into those 4 different categories. Part 3 is models for prediction. So these models are conditional distributions of the form probability of y given x, where x member of big curly x is some input, often high dimensional, and y member of big curly y is the desired output, often low dimensional. Okay, so in this part of the book, we're kind of focused on the idea that there is one right answer that we want to predict. We may have uncertainty about it, but there's one right answer. The next section, part 4, gets into generation. So these models are distributions of the form P of x or P of x given some conditioning C, and there may be multiple valid outputs, okay? So if you say, whatever it is, an astronaut riding a horse, then there's multiple valid pictures of an astronaut riding a horse. Part 5, we discuss latent variable models, which are joint models of the form P of z comma x equals P of z times P of x given z, where z is the hidden state and x are the observations that are assumed to be generated from z. So the goal is to compute P of z given x in order to uncover some hopefully meaningful / useful underlying state or patterns to the observed data. And then finally, part 6, we discover models and algorithms which can be used to make decisions under uncertainty. This naturally leads to the very important topic of causality. By the way, those are his words. I don't know enough to understand why he says that naturally leads to the topic of causality, but causality is usually a good thing. Anytime I've been to a talk or something where people talked about causality, I've learned things. So I think part 6 is relatively short. But so then that covers the 4 different kinds of things. Okay, so there you have it. The layout of the book is going to be fundamentals, inference, and then these 4 kinds of problems. So we hope that by bringing all these topics together, you will find it easier to make connections between all these seemingly disparate areas and can thereby deepen your understanding of the field of machine learning. So that pretty well sums up kind of what I'm hoping for to get from this book, to deepen my understanding and my connections for a lot of things that at the moment I may not realize are connected, but I think are disparate. All right, so let me pause here and just see if there's any comments or questions just about the author's opening 2 pages, opening remarks, and what this book is about. All right. If not, then let me shift gears and talk about what I'm proposing. We've got a good crowd here, and I am certainly, if any of you have been around other events and know, I am very persuadable. So I am definitely open to people making suggestions, tweaks. There's a link just to make sure that you guys all have the link from the meetup. So this is the page for book 2, and right down here you can download a full PDF copy of the book. Just to be clear, the book has not been printed yet. You cannot order a hard copy yet, and it's getting finalized to go to press. So if you're one of those people who saw right when I first published this meetup and you went here right away and you downloaded, you probably don't have the latest copy of the book, okay? Because January 19th is the latest. Now, it may not be that different, okay? But the first time I downloaded the book, it was actually a July 2022 version. And so definitely one of the ones that's like a January version, whether it's the 19th or one of the early ones, some pretty big differences. Okay, so this is, I linked this Google Doc, and I don't want to read through it. That would be boring. But I did want to kind of go over my notion for the logistics and how this session would go. So again, the first book might be appropriate for people who are more beginners. We have lots of beginners. If you look at the other books that we've read, you know, hands-on machine learning, the SQL stuff, everyone is welcome, but I'm just going to be honest and say that, you know, again, I'm hoping that the pacing will be fairly rapid and that the conversation will be a little bit deeper for this book club. So here's the first two parts. So fundamentals, probability statistics, graphical models, information theory, optimization, and then in inference, we're going to talk about different kinds of inference. So after an overview, Gaussian filtering and smoothing, message passing, variational inference, Monte Carlo, MCMC, and then sequential Monte Carlo. So I'm thinking that we can cover parts 1 and 2. It's now the last day of January, so basically through spring. I don't know exactly when it'll be. If we do a chapter week, you know, it'll take us kind of like to May. If we go a little bit slower in certain of these, then it might take us whatever. But so then possibly if people want to stick around, we'll do part 3 prediction over the summer, and maybe in the fall. You know, if some people are gone for summer, fall would come back. Generation, and in particular, I don't really want to wait that long, but I kind of want to go in order. So this is where we'll actually get to talking much more in depth about the diffusion models that are kind of all the rage right now. And then I don't think there's that much necessarily that would directly pertain to like ChatGPT, but certainly language generation is going to be covered to some degree in part 4. So I think I've said that, like, hey, the intent of this is to be more for current practitioners. So if you're someone who's currently a software engineer, you haven't started doing machine learning, you don't know what scikit-learn is, you know, again, everyone's welcome, but I think you're going to have a very hard time, especially not just the fundamentals, but when we really get into some of the other chapters, it's quite math heavy. So I'm thinking we're here, it's Tuesday, we'll meet each week Tuesday. Hour and a half. The ask is that everyone try to do the reading before the meetup. I'm not going to police it, but there's the possibility that if especially it's an area that you're not that familiar with, then, you know, the group might be interested in delving into things, and you're welcome, you know, to be there, but we may not slow down to answer basic questions if those are things that were covered in the book, right? So if there's something you didn't understand, that's fair game. But if it's just because you had a busy week, which is totally understandable, but you weren't able to do the reading, then depending on how things go, just know that there just may not be time for that. Okay. And then I'm going to ask that each week a different person help lead the discussion. So we will take turns. The good news is if most of us stick around, there's whatever, right, 13 chapters. Not everybody's going to have to, but looking for volunteers to share the load, and also just because I think that it actually helps. It helps when people see different styles of presentation, hear different voices, and in particular, different people have more experience. So there's certain sections where I'm hoping somebody will volunteer who knows more than I do on some of these topics. Okay. So that's kind of the general layout. And especially once we get past the fundamentals, the first 5-ish chapters, we may want to take 2 weeks. We may go deep and talk about some papers. If there's actual code for certain things that we want to look at, play around with those. I don't really know how that will go. I think that's all fair game in terms of if a topic is interesting and we want to spend some more time. So at this point, I'm just kind of, playing it by ear a little bit. But so again, meeting here weekly Tuesdays. I don't think there's any big holidays coming up immediately, but so pretty much it'd be every week on Tuesday. Obviously, some people may have things. My work has blown up, so there may, be times people miss things. Historically, at SDML, we have recorded the sessions. And so I would lean to, as the default, to continue to do that, to make it available to people who missed a session. But again, Ryan sometimes gets like kind words where people say, hey, I found, you guys a year ago covered this book. They haven't attended a single meetup. They just go through the YouTube videos and like, hey, this is awesome. I don't know that that's like that'll be such a great way for people to approach this book. I think they're going to want to actually read the book. All right, so hopefully I covered the logistics. Roger, you had the question before. Let me pause here and see comments, questions, requests, thoughts. Where are you guys at?
I'll just say one thing. Right out of the gate, the chapters are a bit long. So the first one is 64 pages, the next one is 74 pages. And then after that, it gets easier. So I want to put that warning out there that the first two are going to be some of the most difficult. So I don't want that to necessarily scare people away. And in these chapters, I've read a little bit ahead. It's useful topics, but you don't have to have like full mastery of everything. So like they spend several pages talking about various different distributions. If you don't know the full math formula of it, if you just understand what the distribution looks like and stuff like that, you'll be able to survive, I think. But I do just kind of want to put that warning out there. And maybe I don't know, Ted, we'll have to talk about this. Maybe there's a different way to chunk it up, because I see that chapter 7 is also only 12 pages. So we've got
the intro to inference is super short. So thanks for bringing that up. So probability is a long chapter. I'm hoping that everybody has some level of background in probability. Yeah, I've noticed every week or so when a new camera ready copy of the book comes out, it's a few pages longer. So yes, so it might be longer by the time we get there. So by me doing the first two sections, that helps break up chapter 2. Chapter 3, statistics. Again, I think most people have at least some background in it, but yeah, I don't know. I don't know if we're gonna actually make it through in a week. I am, as soon as we finish covering the logistics, I'm going to go through the first two sections of probability to give you guys a sense for how I feel we will be able to sort of power through some of the fundamentals, because again, I think you will need familiarity, but you won't necessarily need perfect mastery of all the material. And the truth is, all this stuff, like we could spend 10 weeks on just probability. We could spend 10 weeks on statistics, 10 weeks on, so at some point you just have to like make a call and say, this is how I think we're going to try. All right, go ahead, Roger.
Yeah, Ted, I was going to ask, if it is a live document, is it your intent to just stick with the version that you are linking to currently, or do you want to try to keep up with the latest and greatest?
At this point, I think the changes will be quite minor if we have new additions. So I don't think it'll matter if you stick with the January 19th version, or if there's a February 3rd version. So it'd probably just be like one figure doesn't look good and the author's haggling with the printer to get it tweaked or something like that.
Gotcha.
All right. Fawas, yeah.
Yes, thanks, Ted. Thanks, Ted. Quick questions on the changes in the books, if there is any in the futures. Is there any way to keep track of all the changes made to the books? Like, okay, we just covered this chapter and suddenly there's new material on this chapter or something along that line.
Yeah, I don't know. I'm not the author. I do think it's coming down, even though I appreciated Neil's joke about adding more pages. I do think actually at this point it has settled where we're not likely to see too much new content. But again, I mean, as we come together, if somebody notices something, they can just help share with the rest of the group.
Thanks.
Thanks. Hey, Dave, I see your hand raised.
Hey, thanks. So regarding new editions, I think the way it is progressing from what I see, he's adding more material towards the later part of the book. You can see that there are less chapters, if you may, in each section. And that's where more of the research is happening or advancing. So we may not see a lot of advances in the fundamentals, at least for the next few weeks, for sure, or the spring quarter, if you may. So that was one. The other thing was, even though we will be rushing through this, as you said, some of these foundations will help go past the future chapters much easily if those are well absorbed, because you may suddenly see a reference to exponential family and we can replace it with this, and this is how it works. And yes, you can always refer back to that section and reread it, but if it is read through from the beginning, then that correlation or that association will be much easier and faster.
Yeah, I don't know. Honestly, I don't know.
The math is not going to get easy. I know, Ryan, you mentioned it might get easy, but I'm not 100% sure. Anyway, yeah, that's just my observation, but we'll see as we go along.
Yeah. So kind of how I feel at a high level. This really isn't an answer, but if we're doing statistics or and people start talking about like KL divergence, and then we start talking about other ways to measure, and there's stuff in the book and there's other stuff that's not in the book, and then like I didn't see Earth movers distance in the book, and so like, well, is there a reason why he didn't leave it in there? Is it actually somehow equivalent to one of the other things? And if we have a lot of good rich discussion and we end up spending 2 weeks on statistics, as long as people can be kind of flexible, like I think that's great. That's the whole point of this, is for us to be having like good discussion. What I'm not necessarily interested in is just sort of like again, I don't want to spend the time in the meetup reteaching the material that's in the book, which is pretty much, if you look at our other book clubs, that's like what we've done, So it's like, hey, chapter 2 is probability. Let me now teach all the concepts that were in there, and it's just like a lecture, and you can just skip doing the reading and just take in the lecture, right? So I think as long as we can try to stick to, again, totally happy to answer questions. I'm going to have questions. There are going to be parts that I don't understand. So we will be talking about stuff that's in the book, but as long as it doesn't devolve into just, hey, people didn't do the reading and we're just going over the stuff in the book, then I think the reward will be for the people who did do the reading to be able to get that next level, that deeper, that richer discussion. And if, like, for example, I've heard of Gibbs sampling, I've read about Gibbs sampling, I do not have a very good intuition, I do not have a deep understanding of it. If there is somebody else who does feel like they have a good intuition, good understanding, then, yeah, it'd be great to like have that kind of discussion. So I hope that gives you guys a flavor for what I'm hoping for in terms of how we can use the meetup to enhance people who are reading the book, not just to be like, oh, here's a weekly reminder to go and do this stuff. Any other comments or questions? Yeah, Dave?
Oh, okay. Yeah, I was looking for the raise hand, which is like somewhere there. So are there any problems in this book? As far as I know, there are no, like,
Book one
exercises or
has
anything.
exercises. This one doesn't. He did actually mention another book that has some whatever pen and paper exercises in ML, and some of them may overlap, apply to certain chapters. But again, I think we'll have to see. We'll have to see how that goes in terms of us helping each other make sure that we're walking away with a solid understanding. All right, if there aren't any other burning questions, we're good on time. I think what I'd like to do then is to start talking about chapter 2 again. I'm assuming most of you have not read, but great if some of you have. But again, just to kind of show how I think the pacing can go and what some of the questions might be like. And then I'm secretly hoping that at least one of you will ask a question that I can't answer. So then even though I'm the one that's like talking, I can crowdsource it and say, please, somebody answer this question, because just because I am the discussion leader doesn't mean that I actually know all the answers. I'm not necessarily the expert. In any given week, whoever volunteers and says, I'll take some, they're not necessarily going to be able to answer all the questions. All right, so here is sections 1 and 2 that I did an outline for. Paste this. If you care to follow along, you can pull that up. I don't know that you need to. Let me make it a tad bigger. Or not. Wait. Okay. Hopefully that's a good size. So chapter 2 is about probability. And right off at the very beginning of the chapter, the author recommends some other resources. Okay. So one possibility is Introduction to Probability for Data Science. I have not read this book, but where am I? But the book does look pretty good to me. And so it starts right here in terms of like chapter 2 is the basic chapter on probability, but the whole book really is on probability for data science. So this Stanley Chan book, in the Google Doc, I have a link to this book, the Probability for Data Science website. So you can go and get this book there. So if you're someone who feels that your probability isn't that strong, then this is probably a pretty good reference. The author lists a couple other books, and then one of the last things he references is this Mathematics for Machine Learning book. And I'm curious to see if anybody else has a comment. But I've flipped through this book on a number of different occasions when people have referenced it. And for me, it may just be a personal style thing, but the author's style and their explanations have never really worked for me. So I do not recommend this book to other people. Now, admittedly, Kevin Murphy listed 5 books, and this was the last of them. So maybe they're sort of in rank order. But anybody else either like or dislike this Mathematics for Machine Learning book?
I haven't read that one before, but Coursera just launched a similar course, Mathematics for Machine Learning. And
I think
looking at the chapters are, I think, very similar in order of how they do things as well.
Yeah, okay. Yeah, I didn't think it was based on the book, but maybe it's just the same title. I don't know. But like if I just go to chapter 6, like obviously I need to make this bigger so you guys can see. I just personally am not a fan of of the way the authors describe things. Trying to find like a decent. So I don't know. I mean, this is pretty standard. People talk about sample space, event space, probability, but
Actually, if I can add, I think it's also in Coursera from Imperial College that they have a mathematics machine learning where I think it's the authors that teach them. So I think they reference this book.
oh, so then it is. It is okay. Well, your mileage may vary. It is available at this MML book website, so feel free to check it out. Just because I've not found it to kind of work with my style, maybe, you know, different strokes for different folks. Okay. So again, if you are looking for more stuff on probability, likely next week we'll finish chapter 2, and so I don't know how much time there will be to say, for example, go through the entire probability for data science book, you know, to keep up. But I do think that that is a possible side benefit also, just sort of like building up your reading list of like good resources. And I'm definitely interested when people say, hey, when we're talking about, you know, whatever, Markov Chain Monte Carlo, you know, this is a great article that helps, you know, explain things, or this is a great visualization, like just, again, crowdsourcing, you know, just sort of what people know about where to go, what's a good book, good article, good whatever, that kind of stuff. Okay, so if you're familiar with probability, you know, we have this formal definition of the probability space as this triple. Okay, we have capital Omega, the sample space. We have curly capital F, the event space, and then we have this double strike cap P, our probability measure. And so with this triple of things, then what we do is we you know, define a function on events that, you know, eventually lets us do the intuitive thing that we understand in terms of like probability, right? So for discrete random variables in section 2.12, the author talks about we start with a countable set of outcomes. It could be finite or could be infinite, but it's countable. Okay, and so the definition of random variable is a function big X. And so again, we have our sample space omega, and we are taking you know, events in our sample space and mapping them to a real number. So we could map it to the number 5, we could map it to the number 7. You could imagine like rolling 2 dice. An intuitive mapping might be you count the dots, and so the sum of the dots, that's the real number that you map it to. But technically speaking, you can map any event to any number you feel like. That's just the formal definition, right?
Ted,
Yes.
I don't know how to raise my hand, so if
Oh, okay.
I have
It's
a question.
hidden. It's hidden under, I think, reactions. So you might not think that it would
reactions.
be there, but yes, please fire
Okay.
away.
Okay, so it says that P is the probability measure, which is a mapping from the event E in omega. Isn't E supposed to be in F? F is the event space. It's not in omega, it's a subset of omega. Or is it?
Are you looking at the book, not my outline?
Yes. Probability space 2.
All right. So let's see here. Where are you? Do you know?
Okay, so yeah, it's so it says F is the event space, which is a set of all possible subsets of omega. And E, okay, I was reading it as E is an element of omega, but it's E is a subset of omega. So P does map E in omega to 0, 1. Okay. So as I asked the question, I got my answer, I think. Does that make sense? Do you see what I'm saying?
So yeah, so actually I think your events E are going to be part of elements of F. which I think is what you were saying, right?
Yeah,
There,
yeah.
we use lowercase omega to represent a single outcome that's part of the sample space, right? So like A
Yes.
and B are part of capital omega, but the set A
Yeah.
comma B is not part of omega. The set A comma B is part of F. So I think you're correct. So if the author says part of omega, then that is, I think, a mistake.
No, I'm correcting myself here because E, the way he's written, he said E is a subset of omega, and F is
Oh.
the set of all possible subsets. So
Sorry.
E is
E-
an element of F, but it's a subset of omega.
That's right. That's right.
And
F is
I would
subsets
prefer,
of omega. So any
Yeah.
element of F is a subset of omega.
so I would prefer that to say E is an element of F because P is mapping F into the unit interval. But
Yeah, that makes sense
anyway.
to me. Yeah. So then the possible values for the random variable are its state space, and so again, you can have this random variable x map to whatever real number you want. So you could say I'm only mapping to the real numbers 3 and 5, and that's your state space. Or you could have other different values. We're still in this discrete world right now, so it can't be like, all real numbers between 2 and 3. But it can be a finite or an infinite countable if you have an infinite sample space. So you could have like all even numbers. That would be a perfectly valid discrete state space. And again, I'm vastly condensing, right? I'm not going through the whole section here, but ultimately we have a probability mass function for a random variable, and we will refer to this PMF as the probability distribution of this random variable. But so then here's the main thing is that this probability mass function, so P sub x of A, so this is our probability measure for when, x equals A. And what that is this pre-image, so it looks like x inverse, but it's not an inverse in probability, right? This is the pre-image of A. So I don't know how many, if everybody's familiar with this, I certainly have not been familiar with this for a long time, but so like if you have some function like cosine, right? Cosine, if you say, well, when is cosine the value 1? Well, it's the value 1 at 0 and at 2 pi and at 4 pi, at 6 pi, and negative numbers 2, whatever, right? So you can define inverse cosine over a small range, but as a true inverse, you can only define it over a small range. But when we're talking about probability, if you had, random variable that, sorry, I picked cosine, that's a continuous function, but bear with me, assume a discrete example equivalent. And it was mapping things to, cosine of an input. Then you could have multiple values that would map to 1. You'd have 0, 2 pi, 4 pi, whatever. And so then the pre-image is just all the values, 0, 2 pi, 4 pi, that map to 1. And it is just sort of like I don't know, I'm not going to, mathematicians, like, cover your ears because I'm not going to say this right, but just think of it as sort of the looser, broader interpretation of inverse, because it's not 1-to-1, it's just all the values that would get you to the destination value. Okay. And so then, yes, in the discrete case, we use the term probability mass function, and then we're going to have different names for things in the continuous case.
Pre-image is a generalization of an inverse. You are correct here.
Okay, I didn't say anything too horrible. Good. All right. The continuous random variable case now, typically, we could do, again, arbitrary mappings to reals, but normally we use the identity function. And then we introduce this notion of the Borel sigma field. If you're not familiar with that, basically, I will just say you know, it allows reasonable, useful subsets of the real numbers, but not ones that allow paradoxes. And so if you think about things like the Cantor set or fractals or just really kind of weird things, you're not really going to want to know the probability that the temperature is like some fractal value between 70 and 80, right? It's reasonable for you to say the subset 70 to 75 or whatever, you know, but you're not going to have very bizarre things. So anything that you in the real world would actually care about is going to be allowed in the Borel sigma field. So then we have a PDF and a CDF. They're now continuous. And so in the formulas, you have integrals instead of summations. And then loosely, when we talk about the probability distribution, we're referring to either the PDF, the CDF, or the probability measure. They all are again, there's some technicalities, but they are equivalent to the degree that you can measure them. So they can have like singularity point, you know, differences, but they won't have any area under the curve difference between them. And so loosely speaking, the PDF, CDF, and the probability measure, you can get one from the other. They're all interchangeable in terms of what they mean. All right. Any comments or questions about? Yeah, Faust.
Yes, quick question, Ted. Is the invert notation on the pre-image things applicable to continuous random variable as well?
It is. I don't remember seeing it in the book, but as I recall, they still use the pre-image in both the discrete and the continuous cases.
Yes, got it. I just never seen this notation before. So yeah.
Yeah, it's the generalization, and basically again, you just the goal here is to have one set of notation that fulfills all of the intuitive required things about probability without allowing paradoxes. And in particular, if you do all of this really right, you can use certain notation and you don't need to specify whether it's continuous or discrete. Otherwise, you just have a lot of ugly notation where you're constantly saying this or that, like this if continuous or that if discrete or this if that. And so it's just like, yeah, we just want one set of notation that meets all of the like the stuff that you would learn in high school about probability, but also like satisfies all the most rigorous ways of poking at it and trying to create paradoxes.
It is not only to have good notation. You actually can do a very weird sets which you cannot even draw, but you can describe them. And in particular, there is a famous result in topology when you can cut an orange in such weird shapes, then eventually you can gather them together in the huge sphere, like for example, Earth, and there will be no holes at all. It is a mathematical result. So the Borel algebra, sigma algebra, it in particular axiomized that we don't do this. It should be practical. Our subset should behave like they behave in practice. In practice, we don't have such kind of weird cuts.
Yep. Good. Yes, we don't want that. We want our probability to behave well. Okay. So the probability axiom. So this part probably everybody's familiar with, right? So non-negativity, you can't have a negative probability. Normalization, the probabilities always add up to 1, and additivity. So if you have pairwise disjoint sets, then the probability of it, you just add up all the values, and then from that you can derive the complement rule. So the probability of a complement of a certain set is going to be 1 minus the probability of that set, right? And then the addition rule, when you have events that aren't even disjoint, you subtract the intersection, basically, probability of the intersection. So these are intuitive things that I probably started seeing in whatever, 6th grade math, whatnot, long before I had any idea of like math formalism or anything like that. Okay, conditional probability of event 1 given event 2. It's a probability of the intersection divided by the probability of event 2. And from this, you can derive the multiplication rule, and you can define independent events where you say, hey, they're independent if the probability equals just the product of their probabilities, and the law of total probability, where you sum things based on, if you chop things up into pieces, then you can say probability of X is X conditional on this set of pieces, something like that. Again, might be a slightly different conversation we would have in a future week. If people have done the reading, there might be a few more questions about this, but I think most people have seen, these parts of probability. And so then Bayes' rule famously says, right, probability of event 1 given event 2 is the probability of event 2 given event 1 times the probability of event 1 divided by the probability of event 2. And so then there's the nomenclature used that, I'll be honest, like I use it, but I'm still like not super comfortable just in terms of saying, okay, on the left, we have the posterior probability. And so that equals the likelihood times the prior. And then that's divided by the marginal likelihood. So the probability of E2 all by itself. And we also refer to that thing in the bottom as the normalizing constant. And as I've started to read more and more papers about things like variational inference and, reading some of the stuff about score matching and how like diffusion models are can be shown to be these score-based models. That's really the problematic thing that we run into, is that in order to calculate this normalizing constant, you might need to just integrate over a bajillion things in a way that is just not can't be computed, and we don't necessarily have a closed form formula for it when we're just empirically using real world data. And so really what I started seeing a lot of papers is, how do we deal with not having to calculate this darn marginal likelihood on the bottom, because that's going to trip us up. I was reading something else the other day I wanted to comment. And so I always see things written in terms of this, oh, it's the likelihood times the prior or whatever. But I actually liked this more lay explanation that I just saw the other day. I don't remember where, maybe it was like a Medium article or something like that. But basically somebody said, really what we're saying is that the two conditional probabilities, the probability of E1 given E2 and the probability of E2 given E1, how they are related is by the ratio of the probabilities of events E1 and E2. So if you have two conditional probabilities, like probability of rain given lightning and the probability of lightning given rain, that basically those two numbers will be related by the overall likelihood of rain relative to the overall likelihood of lightning. And I thought, oh, that actually to me is a little bit more intuitive than the more formal thing about, the likelihood times the prior, at least for me.
There is a really cool video from the YouTube channel 3 Blue 1 Brown that explains how to think of this, exactly like you said, as ratios. And really that picture becomes a lot more intuitive than thinking about it like posterior and prior, and because nobody really intuitively thinks like that.
Cool. I've heard great things about 3 Blue 1 Brown. I've only watched a couple, but maybe because I don't have a strong Bayes rule intuition, I think I should go watch that one.
Yeah. They should almost restate that then, or rewrite that then. to split up the two terms and move the division outside.
Yeah, so that's
Or
actually
scaling
how I saw it.
factor.
It was this conditional probability equals that conditional probability, just written full size,
Yes.
times the ratio of those two. And if you
Right.
reverse the order, then you flip the ratio of the two.
Right. I think that you're right. That would be much easier to understand. And it makes a lot of intuitive sense.
Yeah, so like if you just think about it, like rain and lightning or whatever, right? If lightning is much rarer than rain, then you can think about how that's going to affect the two conditional probabilities of rain given lightning and lightning given rain. So lightning just being rarer, then you can just say lightning given rain is going to be a sort of small probability, but rain given lightning will be a much larger probability. Okay, so that's section 2.1. And then we get into section 2.2, some common probability distributions. And you can see here what I did for this. I don't know if you would consider this a cheat or not, but I left out all the equations. And I said, in section 2.2, what the author does is he shows us a bunch of distributions, starting with Bernoulli, binomial, categorical, multinomial, blah, 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 all the way through ones that I am not familiar with. Well, multivariate, Gaussian, and student, okay, fine. But the circular normal, matrix normal, Wishart, and inverse Wishart distributions. I've heard of the Dirichlet distribution, although I can't really say that I have an intuition. I know what that looks like. I think it's one that's kind of like big exponential kind of decay kind of a thing. But anyway, so I'm sure if I knew these distributions better, it would help my understanding at some point later in the book when the author is going to mention them. But I feel like if I don't know them, I can keep going. I don't have to like remember them or particularly know which ones are whatever, fatter tailed and steeper, shallower, whatever, in order to be able to keep reading. So then again, so this is me trying to sort of model how we might go through the chapters. So we're pretty much at time, but I welcome if anybody has a comment just in terms of like, hey, did that seem like that was too fast, too slow? Because again, the idea is not to be teaching you what was in the book. Hopefully, you read that. But by reviewing this is the opportunity for somebody to jump up and say, hey, now hold a second. There was a paragraph in there on Bayes' rule that I didn't understand. Can we go back and talk about that? Or, hey, there was a thing here, or some notation I didn't understand, or whatever. So what do you guys think? Any thoughts? Good, bad?
I have a remark. If people are surprised to see equality with a triangle above it, it is actually a shorthand from lecture notes for mathematics, and it means by this we define this notation to be equal to this formula. And I actually didn't see, I saw it only once used before in a textbook. I'm surprised that he used it so much.
Yeah, actually, you know what? In my notes, there was one place where I was going to switch it to the equal with the triangle over it to say that it's defined as, and then I think I got distracted and I forgot to go and look up and see if in Google Docs that's an available special math symbol or not. But yes, that's a good reminder. So if you see that, it means that not merely the equality of the two sides, but the actual definition of what's on the left side. All right. Any feedback? This is sort of, again, what I'm kind of recommending in terms of pacing as like, we can have an outline, we can have these things, and then people can kind of pause the discussion leader if they have questions, or if they can help, explain something, or even if there's, again, on certain topics, interesting things that we can kind of think about that are deeper. Yeah, Dave, please.
Hey, Ted. Yeah, so I think, the pace was good, and given that there's only 1 week to cover two really deep, complex courses by themselves, if you may. Right. So I like that. The only comment I have is, I mean, for that matter, even he goes through those distributions really fast, and we are compressing that fast pace to even further, compression, if you may. So I think your point about reading it or being on top of it is going to be helpful. And I know you made that several times during this meetup, only because, it can, I mean, that's my part. Maybe I'm not that smart. So for me, if I don't do my reading, it's very hard for me to keep up. But I'm just adding to the same point that you probably have said. But there is a lot of detail for each one of these distributions, and when we read in the papers, there's maybe use sub-Gaussian distribution. Well, I didn't know till I read in this book today that it goes up all the way up to the fourth moment, and that's what it refers to. And I still don't understand its consequence of like what happens when you're doing that or not doing that. But again, that's if you want to go into the details of the math for those in the future discussions, that may be handy sometimes. But again, knowing that is helpful is all I'm saying.
Yeah, that's awesome. Thanks for echoing that. So again, I'm hoping that that you guys are excited and that this format interests you in terms of, hey, this is asking something. Okay, this is most meetups that I go to. I mean, there's some where we do paper reading, and I'd like to try to spend some time with the paper beforehand. But there's a lot of meetups you can go to. You can just show up. You don't have to do any reading. You don't have to do any work. And you can just absorb. And maybe if you did more work, you would learn more. But you're totally cool just showing up. And so what I'm proposing for this series is that we actually do an event where we say, hey, the ground rules are actually the ask is a little bit higher. Okay, so you don't have to understand everything, but if we try to do the reading, then hopefully it'll look a little different once we get past the fundamentals sections. Once we're actually talking about like, Markov Chain Monte Carlo and variational inference, it's kind of a different ball game, because then we'll be able to say like, hey, didn't this model use this, and doesn't so-and-so use this in this paper? And there's just a lot more we can talk about. Whereas I don't know that I'm going to bring anything up when we're just talking about something more basic, like, conditional probability. That's just kind of more of a basic topic. All right, well, if nobody else has objections, again, feel free to contact me. You can contact me on Meetup or on Slack. I recommend, if you're going to stick with us, join the San Diego Machine Learning Slack. We have a book club. I think it's officially called ML-Book Club. But we have a book club channel. Neil already posted some cool stuff there. So like he had a PDF that if you wanted to be able to have the probability chapter, but you didn't want to have to carry around the whole 150 megabyte book, you can do that. Have a couple links. And again, feel free, people can ask questions. We can have different things. So we can use that Slack. And then the schedule is next week. Roger volunteered to finish probability. I have this in my head. I didn't write it down. So the week after that, assuming it's the week after that, Neil volunteered to do statistics. And then Dave, I think you volunteered to do the graphical models, chapter 4. So we've got the first few. I'm going to give you guys a little bit of time to warm up, to decide if you're sticking with us. And then over the next couple weeks, I'll be asking people to say if they'd be willing to be a discussion leader the following week for chapter 5, for chapter 6, and so on like that. And again, asking people to be a little bit flexible. If the conversation goes a little longer, we may not do exactly strictly one chapter per week. A chapter might leak over a little bit into the next, and it might, we'll see. we'll see how it goes. All right. Awesome. So Ryan, if you don't mind, let's end the recording here.